Hello everyone. We are focusing our attention today on integrating powers of trigonometric functions. More specifically, we will be discussing case 3, which involves even powers of sine and cosine. Why would we use any of the methods we will be showing in this video? Well, you have verified first and foremost that the integral is not basic, that substitutions and integration by parts have failed, and that no algebraic methods can be used to solve the integral. Even powers of sine and cosine are cases that involve an even degree for sine or cosine on their own, or in a combination where both have even degrees. If either cos or sine had an odd power, we would return back to case 1 and case 2 in order to solve them. So how does this work? We're going to discuss the procedure by using sine to the power 4 as an example. In step 1, we're going to replace every single cos squared x and sine squared x, so all even powers of sine and cos, by using the double angle identity. As you see, the angle of cos squared x and of sine square x doubles as we apply this identity, hence its name. In our example, sine to the power 4x actually consists of the product of two sine square x's, both of which we are going to replace by using the double angle identity shown above. Before we go any further, it would seem interesting to distribute these different terms and perhaps collect the constants 1/2 and 1/2. So here is our expanded form. The 1/4 in the front is the product of 1/2 times 1/2. Now, in the new integrand, 1 is a straightforward antiderivative, or has an antiderivative that is easy to find. The second term, 2 cos 2x, is almost a basic formula aside for the 2x in the angle. The third term, however, is still a double angle identity, and therefore is still an even power, and therefore we will apply the double angle identity to it once again. The angle 2x has doubled and become 4x as we used the double angle identity itself. In step 3, we'll separate and integrate the individual terms that no longer consist of even powers of sine or cosine. All of the different terms have been split into individual integrals, and the constants have been removed from each one. Now, every one of these integrals is, if not direct, as is the case of the first one, solvable by using a substitution. The middle integral requires a 2, so that 2x as a u has the appropriate 2dx as the du. A 4 is missing in the last integral, so that 4dx is the appropriate substitution, or dw term, for a w chosen as 4x. In both of those cases, 1/2 and 1/4 are there to compensate for changes occurring inside the integrals. And then, after applying the substitution, we can antidifferentiate. The process can be generalized to definite integrals as well. Here is a situation that involves even powers of sine and cos combined. The bounds 0 to pi over 4 are bounds of x. Our first step suggested that we replace all sine square and cos squared terms by their respective double angle identities, and that's what has taken place. Then we have expanded the terms, regrouped the constants, and pulled them out. 1 minus cos squared 2x is actually a trig identity that reduces to sine square x. Sine square x once again, or sine squared 2x once again, is an even power of sine, and therefore the double angle identity has to be applied to it. Once more, constants can be regrouped, and the terms can be separated. Individually, both of these integrals can be done either directly in the case of 1 dx, or using a small substitution for 4x in the second integral. For now, I've postponed integrating the first term. I've adapted the second integral by incorporating a 4, so that choosing 4x in our substitution requires a 4 dx. Outside, the 1/4 is meant to compensate for the 4 inside. And from this point, constants can be regrouped and the antiderivative can be found. Bounds are then substituted into the antiderivative that was obtained.